All right. So tonight, I want to chat about. Last time we talked about hypothesis testing for means and for proportions, and that's all fine and dandy. We're going to review a couple of those real quick. But tonight it's going to be about standard deviation. Okay, same thing. It is. Just like last time, we know what the average should be, what it ought to be, what it used to be. Obviously, we've done something, something's changed, or potentially something's changed. Perhaps we have implemented a new policy, new supplier, new vendor, something, and so we want to know if that's made a change, or we're just quality controlling, and we want to see if the machine has made a change, right? That is, the machine's gotten out of calibration or something, or broken down, or whatever it happens to be. Okay, that's what we're doing on these things always. So, again, last time we talked about, so I don't know, Nate here feels that the average number of oh, damn it. Oh, leave me alone. Of calls per day to 911 have increased. Okay, so apparently he's a 911 guy. It's not just some random bozo off the street. He works in the 911 center somewhere. Probably not just not just an operator. Probably not. Probably someone who's in charge of management, etc. So he's looking into this. Okay. Used to be 100 calls a day. So he samples 50 days. And X bar is 103.7 with standard deviation of 5.9. Okay. And of course, alpha 0.05 is he right? Oh, let's find out. So according to this, if he's right, then the mean is bigger than 100. And when I say bigger than 100, what I mean is significantly bigger than 100. Of course. There's an upper tail test. Somewhere over there is a cutoff. And we're saying we're okay up to 5%. But if you're out here, nah, brah. If you're in here, well, that's exactly what should happen. What we don't know is, we don't know where that guy's going to fall. So we're going to make a z-score, of course, just like we talked about last week. So z is equal to 103.7 minus a honey over 5.9 over the square root of 50. And let's get a little calculator going here. 4.4 standard deviation. So as we talked about last week, if you're 4 deviations above the mean, you are by far a freak show, which means obviously reject H naught is what we're talking about. The number of calls have increased significantly. And of course, it's nice if you give Nate some props. Nate's right. Nate's brilliant. The number of, you can put here, Nate is right, comma. Okay, go ahead and stick that in there if you like. That's what I'm looking for in this situation, right? That's what we're talking about. So then, and we talked about that with means. We talked about, well, what happens if you have a two-tailed test? Okay, and I'm not gonna give you the whole shebang on this one. I'm just gonna review briefly. So this problem was 200. The mean is not 200. That is, this is again typically a quality control setup. This was supposed to be 200. We want to know if it's still 200 or did we mess something up? All right, that's fine. That's dandy. So we take a sample of, 50 things again. Why not? And we find X bar is 205, and we find the SX is 19.1. We'll see what happens here. So 205 minus 200 19.1 square root of 50. And I think we're still going to end up rejecting. How about that? That's crazy. What are you doing, stupid? 1.85. Ooh, maybe not, friends. Now remember, we're not outside the 2 deviation box where I needed to really fool with it. I actually need to figure this one out. Well, I should have did that on the previous problem too. So let's come back here briefly. What we want is how much area is out there. Well, it's basically 0, correct? So in Excel, we'll do this one first. I should have done this one. I didn't ever find the p-value. I know there's basically no chance that it happened, though. I do know that. So what I'm going to do here is equals, and of course it's an upper tail, so I'm going to do 1 minus. Maybe if you put an equal sign there, it would help. Stupid. Try again. Equals 1 minus norm dot s dot dist 4.4. What are you doing? Stop it. Yeah, 0.000005. Yeah, so way less than 0.05. Now on this next one, because it's a two-tailed test, our p-value, remember, has to be on both sides. So when we did this, basically in our minds we said, hey, listen, if you're, again, here this is 0.025, this is 0.025 for a grand total of 5%, right? Now you're like, Jay, I know, I can see the answer now. I know, shh, you're not supposed to see that yet. But 0.05 is because we put part of it on either side. For the alpha value, this is one we need to do that as well when we're finding the p-value. So what you're going to do, and this is very straightforward, you just go equals, and I'm just going to change that one up here. And I'm going to make that 1.85. Right? And so that's 0.03. Okay? And you're like, that's less than alpha. Not so fast, Haas. This is a two-tailed test, so we need to have the 0.03 down here as well, which gives us a grand total of 0.064, which is our p-value. Remember, p-value is the probability that I saw what I saw given h naught is 2, or according to our assumption. Okay, that is greater than alpha, so we're going to fail to reject h naught. And then, of course, we don't know the whole story in this one. I didn't make up a full story this time. I just gave you h naught. And so fail to reject h naught. Now, a lot of times people will screw this up because they're like, oh, yeah, that's less than alpha. But remember, on a two-tailed test, there's a critical value, a cutoff score, if you will, on both sides. From here out is 0.025. And from here out is 0.025. Oops, I'm sorry. Yeah, from here out is 0.025. And so what you have to be careful of is that when you're doing a two-tailed test, you got to remember to get your what you thought your p-value was, times it by 2. All right, whatever. Now, today, what I want to focus on is, what about standard deviation? Is it the same? Same idea? Yes. Same exact process? Basically, but not quite. So we're going to introduce what's called the chi-squared test. Well, the chi-squared deviation, I should say. What are you talking about? The chi-squared. Come on, Jay. You got this. The chi-squared function. Let's do that first, okay? And so just like a normal distribution, it has its own specific shape. But it changes shape based on n. Just like the t-distribution we talked about. That is based on the sample size. Now, can I give you a couple of examples? Sure. Let's try this one here. So if you go in and you go to GeoGebra. Oh, stop it. GeoGebra. Damn it. GeoGebra Classic, that's what I wanted. Anyway, well, the reason I do this is just because it's easy to get a quick visual on what it looks like. Stop it. and you can actually change to chi-squared. As you can see, that's what it looks like. And now the degrees of freedom here are 6. Remember, degrees of freedom, just like with the t-distribution. Just like... Dude, quit freaking out, bud. Stop it. Stop it. Holy buckets. I got seasick in math class tonight because the idiot who was running a computer, or trying to, couldn't figure out how to do it. Whatever, anyway. So just like with the t-distribution, the degrees of freedom is n, sample size, minus 1. Okay? And so you look at that and you're like, oh, that's cool. Whatever. So clearly when I put 45 in, it looks a heck of a lot more like almost like a normal distribution. But when it's really small, it becomes very skewed. Okay? Now, there is an upper and a lower bound of this guy, right? That is, so over here on our normal distribution, we had an upper and a lower bound, right? That is a cutoff on either end, right? That's also true over here as well. I can look for this lower bound. Let's say, for instance, let's say I want to put 0.025 down here. Well, there's a value that makes sense for that. And I could also put 0.025 up here. There's also a value for that. This one down here obviously is smaller than this one because it's not symmetric. We typically refer to this as the chi-squared. That's chi. The Greek letter chi, by the way, is this fella. Chi-squared. So this is our chi-squared. Typically we write it as the chi-squared lower. And this one is the chi-squared upper. Ta-da! Sometimes we want to keep them apart. Okay. Other times, we need to find both of them. Sometimes we just need one. Just depends on, is it a one or a two-tailed test? What's happening? So let's take a look at one. So just like before, I don't know, Caroline, sure, thinks that standard deviation or variance, by the way, I could test for either one. It's the exact same test. The standard deviation for her shift at the plant has decreased. Now, why? I don't know, because she made the kids do a better job before do their work. I don't know. I just work here. Okay, it used to be the standard deviation was 7.1. Sure, I guess. Why not? And we'll write that, of course, this way. And so she samples 37 shifts, apparently, I guess. And she finds that the standard deviation from those is 6.1. Awesome. And yeah, so then at alpha 0.05 is she right? Don't know, let's find out. Okay. No, I heard her say this. That's what I heard. Of course, the opposite is this. It's still 7.1. The opposite, now when I was a kid, I used to write greater than or equal to. I was kind of taught that way. And it was kind of hazy to me. But just if things stayed the same, they didn't necessarily get bigger than 7.1, but they were 7.1. That's what they used to be. Question is, did we reduce it? We probably didn't make it worse. Just saying. Now, how do you find this chi-square statistic, Jay? Excellent question. Thank you for asking it. It's always going to be n minus 1 times sx squared over sigma squared. Okay. Piece of cake, baby. Piece of cake. How do I remember that? It's a good question. I'm glad you asked it. If both of these, let's say this guy and this guy were 7.1, you with me? They're both 7.1. You get a 1-to-1 ratio, correct? And so that'd be right dead in the middle. If Sx, that is the sample, was less than, I would get a value that would be less than 1. And so I'm going to tend to be on the lower side of the distribution. That is, when I draw this distribution up, I'm going to tend to be on the lower side. And if Sx is bigger, it's going to tend to be on the upper side, because Sx squared, S is already bigger than sigma. When I square them, it's going to be way bigger. It's going to push me over this direction. That make sense? So if ever you're wondering, does the Sx or does the sigma go on top, that's how I remember it. Okay? That's how I do it. You do you. Apparently, it is winter allergy season. Nice. So 36, that is my degrees of freedom, by the way, times 6.1 squared over 7.1 squared. Well, Jay, that's going to be a less than 1 to 1. I know, that's why we're in the lower tail. That's because she said it has decreased. You with me? Now, a thing that a guy can do is do this, parentheses, 6.1 divided by 7.1 squared times 36. And you get 26.5. 26.5, if I didn't screw that up. Yay, me. Okay, now, then the question is simply this. We have a distribution doing some number like this. Don't know, don't care. Okay, 26.5 is, I don't know, somewhere here. And we're going to find this amount. How do you do it? Well, CDFs, baby. CDFs equals. And now this is a big deal. Okay, now I'm going to show you a couple ways to do this problem. I'm going to do equals chi-squared dist. Now, I just use chi-squared dist. You'll see that there are several of them. This is the one I do because to me it makes the most sense. Because otherwise, you have to learn 18 different ways of doing things, and I just not into that. Okay, and I got 0.12. Now, if Jay, you're like, I don't know my way around the chi-square distribution. How do I know if I'm like on this, if I'm on the lower end of half or not? Well, I'm promising you on the lower end of half because your SX is smaller than sigma. Yes, I promise you. I'm not going to lie to you about that. I got you. Okay, but if you would play the game I just did over here, and you got a number bigger than 50%, guess what? You're on the upper side of the middle. That makes sense? And so just kind of keep that in your head as we're going along here. And just be aware of that. In fact, what would happen? Check this out. What if you put 36 here instead of 20? Oh, stop it, you hippie. What if you put 36 right there, where that guy is? Ooh, that's like right in the middle, Jay. Yeah, it is. Well, because that says it's a 1-to-1. Yeah, it is. And so you can kind of see it. Now, it's not exactly perfect, you with me, but it's pretty close, right? So kind of keep that in the back of your head as you're going along. That helps you decide whether we're there, whether above it or below it. Now, again, P is 0.12. Well, that's bigger than alpha, so we're going to do what? We're going to do fail to in other words, there's a 12% chance of that. Our BS level is 5%, so we're going to fail to reject H naught. And then what happens here? Caroline is wrong. Sorry. Not sorry. The standard deviation has not decreased significantly, right? Now, it's possible it is down a little bit, but it's not a significant amount, okay? And so when we say that, when we say significantly, what we mean is, hey, this is a statistically significant event. In other words, there's such a small chance that's happening, we think it must have changed. We're going to conclude that it must have changed significantly. It wasn't just some random one-off that we saw. I know what you're thinking. Jay, show me more. Okay, I got you. We got this. Now, Suzanne, good for her. Suzanne believes that the variance of the number of 911 calls has increased. Used to be 10. Nice. So she samples 20 days or shifts or whatever. I don't know. I didn't ask her if it was days or shifts. We're just going to go with days, I guess. And sees SX equals 13.7. Nice. So add alpha 0.05. Is she correct? I don't know. Let's find out. So I can always make my chi-square distribution. I probably should always start off with my hypothesis test, though. I heard this. So her chi-square test is going to be 19, 13.7 squared over 10 squared. $35.66. Again, if this was a 1-to-1 ratio here and here, you get about 19. That puts you right pretty much smack dab in the middle. We're bigger than that. Yay! Again, Suzanne's kind of a moron. If she samples 20 odd days and she gets less than 10, and yet she somehow still thinks it's greater than 10. You with me? That's weird, right? She's been watching. She's like, geez, it is getting bigger. The question is not, does she think it's getting bigger? The question is it a significant difference? Or is it only just a small amount recently? And I'm not judging her. I'm just saying that if a person was saying, hey, listen, I feel like it's really changed. And so you could take a sample of 30 days or, whatever it is. It doesn't even matter. And you're done and you're like, oh, look at that. See, I was right. Wait, from my sample, I got from the average of my sample, or the standard deviation of my sample, is less than what it's supposed to be. And somehow yet you're going to try to tell me you think it's gone up? Bro, I don't think so. So here it is, chi-square dot dist. And again, I'm just going to type it in the way I want to this time, and then we'll come back and you're going to go, oh, you dummy. So 35.66, comma, degrees of freedom was 19, comma 1. And you're like, whoa, it's like 98. Oh, dummy. That's because you're in the upper tail. That's right. So I should have done, right? 1 minus. And so there is a 0.01. So my p-value here is 0.01, which is, of course, less than 0.05. So we're going to reject H naught. Suzanne is correct. There's 2 R's in there. The standard or the variance has increased significantly. Oh, by the way, pay attention to this. Now, this is classic Jay tries to screw with people. Ooh. Suppose I take that exact same problem to see if you're paying attention. This guy I used to teach with, he died a few years ago, but he used to always scream at the kids, it costs you nothing to pay attention. And it's kind of funny. It's a Todd Smithism. Now, the variance is this. Now, pay attention. A lot of times they will, if they're talking about the variance, they will quote you the variance. In other words, oh, the variance is, the variance is 10. Okay, well, that's sigma squared is 10. But here's what ends up happening. You take a sample, and from the sample, you actually compute Sx, let's say. Now, here's where it gets a little funky and weird. Like the Sx squared was 4. Now, what are you talking about, Jay? Come on, you jackass. It was 12, rather. Sorry. Now, if you were to set this up, or let me back the train up here. You may be told this. Jay might be very confident in telling you this problem here. And you're like, oh, right on. So this is what happens. Watch. Chi-square equals still 19. And you're like, all right, times 4 squared. All right, times 10 squared. Uh-oh. Remember, it is Sx squared over sigma squared. And what I just did to you is I gave you sigma squared. So don't square it again. Make sense? Pay attention to that. Be heads up to that. Okay? I'm not opposed to doing that to see if you're paying attention. Okay? But just be aware that can happen. It does happen occasionally. You'll see it. Because again, we don't, in Excel, that's not 100% accurate. A lot of the programs won't tell you the sample variance. They'll tell you the sample standard deviation. Okay? Now, in Excel, if you do summary statistics on a whole list of numbers, it typically gives you both. But I'm just saying, it's possible that you only get the standard deviation. Okay, and yet Suzanne asked us about variance. Just pay attention to that. All right. Yeah, I don't know. So we want our standard deviation to be 2.7 on this machine. Okay, so to do quality control, sample, I don't know, 35 items. SX is 2.3 at alpha equal 0.05 has sigma changed significantly. I don't know. Let's find out. Two-tailed test, again, quality control. You're doing this versus this. Two-tailed test. Let's go. Bam. So, that looks terrible. I can't read that. So, it's 34. 2.3 squared over 2.7 squared. Again, it's going to be in the lower part of the tail, but it's a two-tail, so whatever I get, got to times it by dose. Okay? And so when I look at this, I'm like, all right, let's pull out the calculator here. So 34 times 2.3 divided by 2.7 squared. 24.67. Is that likely to happen or not? I don't know. Let's go ask Betsy. Oh, Betsy. Equals. I'll probably do it in two pieces just for fun, I think, because I think it's nicer. Sometimes to see what's going on. 24.67. Common degrees of freedom was 34. Common 1. That's 12%. Not so fast, Haas. This is a two-tailed test. Dude, there's a 24% chance that I just saw this. What do you mean it's 20? It's a 24% chance that I just saw this happen, given that this is true. Well, that happens all the time. It's like probably throwing two heads in a row on a coin. That happens literally all the time. So what are you going to do? I'm going to stick with H naught. What does that say about our machine? It must be working properly. The machine, the standard deviation has not increased or has not changed significantly. Nice. Now, another question that you might ask is, Jay, what if I wanted to know something about the standard deviation of the wingspan of butterflies? I don't know. Probably got to go take a sample of them, though. And maybe it may say I want to make a 95% confidence interval for the wingspan deviation of butterflies. And you're like, wait, so not the average. Correct. So what am I going to do? Well, I'm probably going to go sample some. So n equals, let's say, 40 butterflies. Now, of course, I can, if I want to, give you X bar. Matter of fact, I think I'm going to. Oh, look at that. 10 centimeters. All right. Standard deviation is 16. No, 16. Wait, 16. Pull your head out of your butt, Jay. 2 centimeters. Awesome. Nice. Now, you're like, I don't need that. Okay? When I do this problem, and I'm going to write this down, but I don't want you to get all weirded out by it, okay? So I'm just going to do this. I wouldn't write this down. Again, we mentioned this previously. This is a lower. And over here somewhere we have an upper. If I'm doing this 95% in the middle, obviously you're going to have 0.025 and 0.025 up here. Okay? I can't do it just exactly like I did it before with the z-score, but I can do it kind of that way. Now watch this. Oops. It's not negative z, it's just chi-square lower is going to be less than or equal to, now this is where it gets kind of funky, n minus 1 times sx squared over sigma squared. And then and then, oops, what are you doing, stupid? Chi-square upper. Now, first thing I'm going to do is I want to solve for this fella. And I don't want him on the bottom when I do it. Okay? So what I'm going to do is I'm going to flip everybody. Okay? But remember, if this was something like 9 and this was something like 7, when I flip them over, the arrows go the opposite direction, yes? Because 1/7 is bigger than 1/9. And so what's going to end up happening is going to be 1 over sigma, or chi-squared upper. And then it's going to be in the middle, it's going to be sigma squared, n minus 1, sx squared. By the way, neat and write this part down. I'll tell you when I get to the part where you should write it down. Oops. Nice. And then you simply want to solve for chi-squared, or for sigma squared, rather. So you're going to have n minus 1 sx squared over chi-squared upper, sigma squared. And this is the confidence interval for variance. And if you want standard deviation, just square root your answers when you're done. It's that easy. Okay, this is what you want to know. Okay? Escape. So we went out and sampled 40 butterflies. So it's going to be 39. 39. Cool. And then we need to figure out, what else do we need? Sx was 2. So it's going to be 2 squared. 2 squared, whatever. Inside, outside, call it 4. I don't care what you do. Now I need those lower bounds. So up here, this is 0.025. This, from here down, is going to be 0.975, correct? So you're like, oh, we need an inverse chi-square. That's right. Nice job, pal. Nice job. But unlike with the normal distribution, on the normal distribution, if I put in 0.025, I got negative 1.96, and then obviously positive. This one here, I actually do have to do a little bit of work. So 0.025. And then our degrees of freedom here was, I can't remember. Our degrees of freedom here was 39, is that right? Yeah, 39. So 23.65. That's the lower. But how do I know which side it goes on? Okay, I'm going to let you on a secret. The numerators are the same. You with me? Your two chi-square numbers are going to be different. And so, like, I don't know which one's which. I'm so confused. Just get them both, divide them, put the bigger one on the upper side when you're done, yes? In other words, when I do this number here, I'm going to get a number. When I do this number here, I'm going to get a number. Whichever is the bigger one, put it on this side when you're done. It's that easy. Don't overthink it. Don't stress. For heaven's sakes, it's just a math problem here, okay? Here we go. So 39 times 4. Oops. Divided by 23.65. Is 6.5. So 6.5 on this end. And on the other end, it's going to be, oops. Oops. Ta-da! Oh, you hippie. 2.68. Yay! There's the confidence interval for your variance. If you want the standard deviation, you simply square root them both. Again, I got 6.5, and I don't know if 6.5 is bigger than 2.8. Well, yeah. So just, it's not rocket surgery here. You got this. I have faith in you. So 1.64, if you square root this guy, and if you square root the other guy, come on, get up there. Get up there! Judas Priest. $2.56. Yay! And so it's the exact same deal. Don't want to not. Jay, could we, on the previous problem, instead of doing a two-tailed test, could we have done a confidence interval? That's a great question, bud. Let's find out. Let's find out. I don't know. Yes, I do. That's a lie. I know the answer. It's going to be like this. So it's going to be, what did I say the top was? 34 times 2.3 squared. This is a two-tailed test, so it works for this one. It will not work on a one-tail. Never works on a one-tail. But feel free to use it on an upper tail if it makes you happy. Now, got to go back to Excel, obviously. And I'm going to put in here, again, this is a two-tailed test, so I don't want to change that guy. But what I do want to change is my degrees of freedom, which is 34 this time. And I got 52, basically. And then on the other end of it, put a 0.025, 19.8. So if I divide them out, .08 on the top end. On the bottom end, calculator stupid, come here, attaboy. You got this. I got 3.45. Yay! And then, but listen, Jay, I want a confidence interval for this, for the square root, or for the standard deviation. Oh, okay. So I got 1.85. And on the top end, .013. Yay! Now let's go look at our hypothesis. Bam! Look what lies in here, friends. Under H naught, sigma was equal to 2.7. OMG, gosh, it's in the middle, where the unknown sigma would be in most of the time, right? Like what, 95% of the time. So what are we going to do? We're going to stick with H naught. Again, that's just a different way of doing it. If that makes you happy, friend, you go ahead and do it. Be careful that we were talking about standard deviation in the H naught, so you make sure you square root this guy. If you're talking about variance, obviously don't square root the guy. Okay, that's the only thing you can kind of get a little hung up on sometimes. So just be careful. Don't fall into that trap. All right, have a nice week.